So hello everyone. Today we'll be starting with the week 3 and week 4 combined of the course linear dynamical systems. So in this course we will cover both these topics, controllability and state feedback. So in this module basically we have combined both the weeks, week 3 and week 4, because the idea is that most of the concepts which we will study for the controllability, they would be directly applicable for designing the controller, particularly the state feedback controller, right? So this would be the outline of the overall week 3 and week 4. We'll start with the controllable and reachable subspaces with a brief introduction about the controllability. Then we will review the fundamental theorem of linear equations, which would play a key role in the results we would going to discuss in the later topics. Third is we'll see the various tests for controllability, followed by the decompositions, and then the concept of stabilizability. So the first 5 bullet points basically talks about the controllability in overall. The last 2 points, 6 and 7, where we study the problem of feedback controller design, and also we would see the regulation in the tracking control problems as a part of the week 4. So starting with the simple illustration of controllability. So the idea is, let's say we know the how we define the state of the system. So from the beginning we have been using this variable x. Either we are dealing with the linear time invariant system or the time varying system. So the idea is, let's say we pick two times, t is equal to t0 and t is equal to t1. And at these times we compute the value of the state, let's say x t0 and x of t1. Okay, so suppose these points are marked at t0 and t1. Okay, so now the idea here is that given the value of the state at time t0, which is x of t0, we want to take this state trajectory or the signal to a point which is defined by x of t1. Now the idea here is that to go from t0 to t1, if there exists any control signal, because with the help of the control signal we want to take this trajectory from the point x of t0 to x of t1, right? So this determines that whether my system is controllable in general or not. Okay? Now in the last week we have studied a concept of the stable systems. Now in the stable system we studied two concepts. One is the asymptotic stability and one is the exponential stability, right? Or the marginally stable system. So in the marginally stable systems we have understood that the signal or the state trajectory would not go towards the zero, but it would be bounded or it would settle down to some value. Now here the concept of controllability is a bit different from the stable or the stability. It should not be confused with the stability, first of all. Why? So here the idea of controllability, once again, that to go from xt0 to xt1. Now after this t1, how the trajectory or where the trajectory will go, this is not in our control. And in fact, to go from t0 to t1, there could be number of paths. So let's say this is one path, this is another path, or this could be another path, because we want to reach from x of t0 to x t1 anyhow. Now what would happen after this? This is not considered in the concept of controllability. So these two, because in the stability concept we want to ensure that the system, if we are talking about the asymptotic stability, should settle down to the zero value, right? So these two times are particularly important for the concept of controllability. So after seeing this simple illustration of the controllability, let's try to put all these things in the formal framework. So we'll start with the linear time varying systems, and then we would tailor all the results for the LTI systems. So consider the continuous time LTI systems where the AT, BT, CT and DT are the time varying system parameters. So we know that in the first week we saw that using the variation of constants formula, a given input u transfers the state x of t naught, which we have defined by x naught, initial condition at time t naught, to the state x of t1 at time t1. And this is the formula we have used to compute the signal x1. Here we have specified at t is equal to t1. Okay. So where we also know that this phi defines the system states transition matrix. So here we want to express how powerful the input is in terms of transferring the state between the given two states. So let's see the definition of the controllability. So the LTV system is said to be controllable at time t naught whenever there exists a finite time t1 which is greater than t naught, such that for any initial condition x naught and given any x of 1, there exists an input u that transfers x naught to x1 at time t1. Okay. So this is the same thing what we had seen in the previous slide. And otherwise, if the system is not, if there does not exist any control signal which could take the state trajectory from the value x naught to any x1, then we say that the system is uncontrollable at t naught. So this definition is particularly for the LTV system. Now if we want to tailor this definition for the LTI system, so we say that the LTI system, if the system is controllable, if we somehow proves or shows the existence of the control signal, that the state equation is controllable in the time invariant case, then it would be controllable at every t naught and for every t1 which is greater than t naught. Right? But for the time varying case, these two specification of the times t naught and t1 is pretty much crucial. And once we develop the concrete results to test the controllability of the system, you would notice that how these times t naught and t1 are playing the key role. Okay. So now we will define two subspaces. So the idea here is first basically defines the controllability from the origin, which we also say, or which is also equivalent to saying the reachability. Okay, and another one is the controllability to the origin. Now the broad concept of the controllability is to steer the trajectory from x of t naught to x of t1. Now when we speak about the controllability from the origin, now here the x of t naught is basically 0. So we want to go from 0 to some given x of t1. Now the controllability to the origin, that given x naught, we want to go to x naught. Now the second definition should not be confused with the concept of stability. The stability says, first of all, the controllability to the origin is not at all equivalent to the stability. Let's recalling the concept of stability, that we want the state trajectory to reach to the origin when t tends to infinity. Okay, for the asymptotic stability. But controllability to the origin says that the state could reach to the origin in some finite time t1, but whether it would stay after there, this is another problem. Okay. So here we would define reachable space, that what all state variables at time t1 could be reached starting from the origin, and controllable subspace which defines that what are all the initial conditions from where I could reach to the origin in some finite time t1. So given two times t1 which is greater than t naught, greater than or equal to 0, the reachable or controllable from the origin on this time axis or time interval t naught t1, we define the subspace R t naught comma t1 consists of all states x1 for which there exists an input u within the same time interval that transfers the state from x of t naught is equal to 0 to some finite value x1. Okay. That is, so this is how we define the reachable subspace R T0 comma T1, which contains all x1 which belongs to the n dimensional space, okay, such that there exists u, so that I could obtain this, or which follows this one. Okay, so this x1 and u pair should satisfy this equation. Now for the controllability to the origin, we define by this mathematical environment consists of all the states x0 for which there exists an input u that transfers the state from x0 to 0. Okay, so here it would, so the subspace consisting all those x0 in the set of n dimensional, or in the n dimensional space, we say that there exists a u such that x of t1 is equal to 0 is equal to this one. So this part was not included in the first definition of the reachable space because x0 is equal to 0. So when we put x0 is equal to 0, we did not have anything here, and the rest of the part remained the same. So here this x0 and u, this pair should satisfy this equation. Okay, now let's see a bit detail into characterizing these spaces. Before that, we see that the matrices C and D play no role in these definitions. Okay, so generally we talk about one talks about the controllability only of these state equations, or we say the pair A comma B. Okay, now for the controllability, most of the time we won't be including the output equation. Okay, but it does not mean that the output equation is not there. So we can see some equivalence or some similarity and differences between the two subspaces what we had just introduced. So determining the reachable subspace amounts to finding for which vectors x1 the equation is satisfied for some u. This is the same equation we had seen earlier, which comprises the reachable subspace. Okay. Now, similarly, determining the control subspace amounts to finding the vectors x0 for which this equation is satisfied for some u. Okay, now I use the same equation here. Now, if I rewrite this equation, let's say by taking this part onto the left hand side and then taking the inverse of the state transition matrix, or pre-multiplying by the inverse of the state transition matrix both sides, I can take the inverse because we knew from the first way that the state transition matrix is non-singular. Okay, so in this way I would obtain x0 is equal to minus phi inverse d tau. We missed something. Okay, so this plus sign won't be there, sorry. Okay, so this equation I would obtain. Now since this integral is over tau, I can take this part inside the integral, and then using the property of the state transition matrix, I could replace the multiplication of these two state transition matrix by this, where the final time is being changed from t1 to t0, and we got this negative sign, and this negative u or minus of u I have replaced by another signal v, so that I could write this compact expression in terms of x0 only, which is quite similar to x1, with a slight difference that in the state transition matrix the final time here is at t1, while here it's t0. The state transition matrix, if we recall, that the input has been applied at time tau and the response we are getting at time t1. Now here, since in the continuous time we could replace, or either we could go forward or we could go backward for representing the state transition matrix. Okay, So both the expression almost looks similar, with a slight difference that the time t1 in the state transition matrix here has been replaced by time t0. Okay, with u being changed to v, where v is basically the negation of the actual control input. So let's consider some examples to better visualize these two subspaces. So here we are seeing a parallel RC network where in one branch we have the series combination of R1C1 connected in parallel to another series combination of R2C2, and both of them are being powered by a common voltage input by U. So if we write the state space model of this parallel electrical network, we obtain this state equation, where this is the A matrix and this is the B matrix. Now the solution, by using the variation of calculus formula, we obtain this solution independently for the two states. So first of all, visualize this state space equation. So in the A matrix, the elements are only present on the diagonal, while the off diagonal elements are 0. So either I could consider them two independent systems, or as one system where it is already diagonalized. Okay, so writing the solution to this system, this is the solution which you can obtain readily. Now in this formula, if we have a couple of conditions, that is to say that when the two branches have the same time constants, that is 1 by R1C1 or R1 is equal to 1 by R2C2, let's specify them by some other variable omega. So these two time constants are basically appearing here in the state transition matrix. Okay, so if I replace them by omega, I get this simplified equation, because this e to the power minus omega t would be a matrix. And since they were the two independent solution, I could express, see, if this R1 and C1 and R2 and C2 both are similar, I can take the common part R1 C1 from this matrix, and the rest of the matrix would be a vector of 1 and 1. This is what I have expressed here. This is just a simplification version of the previous equation. So now if we apply that formula, that is to say if I put x0 is equal to 0, then x of t basically reduces to this equation where alpha of t is defined by this. Okay, so here I put x of 0 is equal to 0, this part goes to 0, and the remaining one, by specifying this whole part by some alpha of t, we get this simplified expression. So what it says, that there could exist input u which could transfer the system from origin by putting x0 is equal to 0 to any other state with where the state has to satisfy this constraints, x1 is equal to x2. Now if I want to reach, so what does it mean, that let's say if the state x at t1, they should be same. If I am having the value x1, it should be x1. Now if I want to reach to another value, let's say x1 and x2, which are defined by two other different times, then I cannot reach. So this is controllable under this condition only. So we define the reachable subspace of the system as this one, alpha 1 and 1, such that alpha belongs to a set of real numbers. When we put t is equal to t1 here, this becomes a proper definite integral. That's why it belongs to a set of real number. Okay, now in the similar way, we can compute the controllable subspace, which says that we want to transfer from x1, x of 0 to the origin. So we put x1 is equal to 0 with a non-zero x of 0. Okay, now again this part would appear as it is, this alpha of t. Now the simplification, what we had seen by when we had seen some similarity and differences between both the subspaces, I could again express this controllable subspace as this one, where this alpha could be another value, but the space would remain the subspace would remain the same. So here we obtain that when 1 by R1 C1 is equal to 1 by R2 C2, we obtained a constrained subspace, the reachable subspace and the controllable subspace. So now if we see that if this condition is not satisfied, that 1 by R1 C1 is not equal to 1 by R2 C2, then you could also test by yourself that any vector in the two-dimensional space can be reached from the origin, and the origin could also be reached from any initial condition in the two-dimensional space. Okay, so that is to say that R T0 comma T1 is equal to Ct comma T1 is equal to the entire two-dimensional space. Okay, so this you can verify by yourself if you have any parallel network, and the time constants of that parallel network are same, then the system is not completely reachable or controllable. But if the parameters are not equal, then it is completely controllable. Okay, so let's see another example or another application to visualize or characterize these two subspaces. So we have this setup where some mass m1 is connected to the parallel combination of the damper and the spring. A similar system has been shown here with m2 b2 k2, and these two systems are connected by a rod on which the control or the u is being applied. Okay, now if we try to model this system, we obtain this AB matrices. Now if you give a close look to this particularly A matrix, so I can combine this block and also try to visualize this block. Okay, so again we see that either I could consider both the systems separately. It shows that both the systems are connected in parallel with the common input u. Okay, and the off diagonal block matrix is a zero matrix. Okay, so again, if these parameters m1 b1 k1 are equal to m2 b2 k2, you would notice that the system is reachable and controllable under the constraints that x1 x2 is equal to x3 x4. Okay, now if these two parameters are different, then the system is completely controllable. So if we want to generalize this particular scenario, let's consider the summation of or the parallel interconnection of two subsystems where these matrices A1 B1 and A2 B2 producing the output Y1 Y2 and sum them up by Y. Okay, again we could express the state equation using this A matrix where A1, A2 are the block matrices and similarly the zero matrices and their corresponding input distribution matrix B1, B2 with the multiplication of U. Now again if A1 or A2 are equal and B1 and B2 are equal, again you would see that the system is controllable to the origin and controllable from the origin under the constraints that x1 should be equal to x2. Okay. So this shows that if x0 is equal to 0, we cannot transfer the system from the origin to any state with x1 is not equal to x2. This is what we have also seen in the previous examples. Similarly, to transfer a state xt0 to the origin, we must have these constraints that both the state would either reach or would the initial condition would remain the same. Now talking about the cascade connection in general, so we see that parallel connections of similar systems are a common mechanism that leads to lack of reachability and controllability. So this is what we have seen in the previous examples. Now if we talk about the cascade connection, they generally do not have this problem, but they may lead to stability problems through the resonance. This is what we had seen in the week 2 slides or week 2 lectures. Okay, so this parallel combination is you could see in many industrial processes where particularly in chemical process industry where you have the multiple tanks are being supplied to the common control input. So there could be, this could lead to the lack of reachability and controllability. Okay. So one more example we could consider here. So let's see, we are given this electrical network where we see the four resistors are connected, when which are connected by this capacitor. Now in this electrical network we define the state variable x, which is the voltage across the capacitor. Now if x of 0 is equal to 0, if the voltage across the capacitor at initial time 0 is equal to 0, then the trajectory x of t would always remain 0 no matter what input you apply to the system. Right? So this should be careful, because when we speak about the two subspaces, reachable subspace and controllable subspace, we particularly the reachable subspace, where we want to go from 0 to some finite value in finite time. But here, depending on the circuit, if you are starting with 0, it might be possible that you will never reach to a finite value. So this is particularly due to the symmetry of the network, and the input has no effect on the voltage across the capacitor. If you recall your basic measurement course, this is a bridge network where the current will never flow in this middle branch. Okay.